So as we start to think about nitrogen, I wanted us to spend a little bit of time and just do a brief review of the nitrogen cycle. Specifically, I want to talk about our inputs, our additions, and then how we can be losing nitrogen from the soil. So as we start in with our additions, it's the basic idea of just our commercially available fertilizers. Maybe you're dealing with a producer that's putting manure on. You might be dealing with a legume crop and we have biological fixation. And then we really dig down into the soil itself and we talk about this idea of mineralization or nitrification. The idea that we're moving from organic matter to ammonium and then from ammonium into that soil nitrate. However, while we have additions that are available, we also have the potential for loss from our soil nitrogen cycle. Those are going to be the key ones that we're going to talk about. We're going to look at the idea of leaching, that negative charge of the nitrates moving the nitrogen down through that soil profile, exiting the rooting zone where it's no longer going to be available to your crops. Or we can have denitrification, we're losing the nitrogen back to the atmosphere. We have volatilization, right? Again, we're another source of losing nitrogen to the atmosphere. And then the last one is immobilization, where we're locking it back up into that soil organic matter. So what I want to focus on today is what we call our XN technology, the accelerated nitrogen technology that we find within some of our nitrogen management products. One of the key statements about our XN technology says that we are maintaining nitrogen placement, right? So as we think about placement, the key word there is keeping it within the rooting zone. However, it's not just that we maintain nitrogen placement, we are doing it without disturbing soil biology. So kind of the two key parts of our nitrogen cycle. We're doing the additions, but then we are also not disrupting all of the bacteria and fungi that are going to be cycling that nitrogen within our soil profile. So when we think about how are we going to apply this to where we are today, I think about some common conversations I have with some of my clients. And those questions that come back to the idea of what investment are you making in nitrogen this year, right? And so as we think about fertilizer dollars, we know that is a substantial investment per acre in terms of the amount of nitrogen that we're going to be putting on. We have to follow that with a second question, which says how much of that investment can we potentially lose either due to leaching or volatilization? And then we follow that last one with, what can we do to help you reinvest your dollars so that you get better use efficiency of the nitrogen dollars that you're already putting in to your crops? So as we start to think about where are we going to be seeing this, it's going to be all the way across the board in all of the different forms of nitrogen that we use. Urea, anhydrous ammonia, and UAN. All of that is what we're going to be looking at in terms of maintaining that soil nitrogen. So as we start to look at how do we do this, what is the background, and what does science say, we really are going to be looking at two different experiments. And the thing I love about these experiments is they were conducted by third parties, so there's no bias. So we're going to be looking at these third-party experiments that were conducted over a multi-year time frame. So we get to see the idea of wet, we get to see the idea of monsoon rains, and we even pick up some drought time. So we get to see it over a multi-year in two completely different settings. So the first one we're going to look at, we had up at Central Lakes College in Staples, Minnesota. Really nice sandy area for those of you that are up there. And the second one that we're going to look at was from the Irrigation Research Foundation out in Yuma, Colorado, which was an irrigated setting. So again, multiple years, third party, and so we have no bias in that data collection. So let's start in with our Central Lakes study. All right, so when we step back, whenever I come in and I look at a research experiment, I love to take a step back, take a 30,000 foot view, and see what we have set up. So when we go up to Central Lakes College, we ended up with two different treatments. We have our first treatment, which was Enzo Max treated. So as we're looking at this map right through here, it's this top portion of the map that's labeled as treated. So whenever you hear me say treated, or we think about what's happening in this upper portion of the field, N-Zone Max has been applied to our nitrogen additions. The second treatment was what was called the control. When you hear control, I want you to think untreated. So we were not adding N-Zone Max. All right, so that's the basic design. So now let's talk about how are we collecting data. So we went in and we installed 2 lysimeters. So the easiest way I like to visualize a lysimeter is it's a way for us to pull out the groundwater at different depths to measure soil nitrates. So we were installing lysimeters at 4 feet and at 6 feet. That is going to be from the surface going down. And again, visualize when we think about that. That's how we pull. We're literally going to create a section and pull the water out of the ground. The third way that we monitored what was happening with the soil nitrates was actually going down to the groundwater table, and we were going to be pulling samples up throughout the year. What I want us to focus on with our collection points is what is called monitoring well 2 and monitoring well 4. So MW2 and MW4. Right now, what I want us to just ingrain into our mind is anytime I talk monitoring well 2, or we look at some data, that is from the control, which was the untreated, so no N-Zone Max. When we look at monitoring well 4, it's going to be found in the upper portion right here. What I want us to think with monitoring well 4 is this was treated with N-Zone Max. So this is going to be on the treated side of the field. Just to kind of give you a visualization of what was happening, right? They were coming in, they were actually boring down on the monitoring wells until we were hitting the groundwater, and that way they could pull their subsamples out. And the other lysimeters would have been pulling those soil samples out at our depths of 4 and 6 feet, so we could actually see what was happening within that pore water, or the water that was going to be available to the plants. So first of all, we start to collect a lot of data. And I know a lot of times when we start to look at data, we think, man, this is a lot of numbers. I don't really see everything that's going on. So whenever we put data up on the screen, I want you to do this with me. I want you to take a step back, and I just want you to look at trend lines. So let's start to talk and let's start to look at what we're going to be seeing. So first of all, let's talk about all these different colors that we have going on. So anytime we see the brown line, we see it right through here, we see it right through here, that is monitoring well 4, a lysimeter at 4 feet. Okay, remind ourselves, monitoring well 4 was the N-Zone Max field. So the nitrogen had been treated. So we want to keep that in mind. Then we have this light yellow and this light blue line. The light yellow and the light blue line were the monitoring wells on monitoring site 2, which have been the untreated. And so what we're looking at here is the field then that did not have N-Zone Max that was applied to it. But again, we're really going to focus on our brown and on our yellow, right? Brown being N-Zone Max treated, yellow being the untreated field. And the first thing that we see is we definitely have variation over time. But as we started to dig into the data, what we found is that year after year after year, so 3 years of the experiment, we started to find the exact same pattern on the N-Zone Max treated field. And the pattern that we saw each year on the N-Zone Max treated field was that we were holding nitrates in the rooting zone at 4 feet compared to the untreated side. In fact, when we look at the difference, we're looking at a 3 to 4 times increase in the soil nitrates at a 4-foot level as compared to the untreated side of that field. So that starts to tell us, as we look at patterns, that what do we see? That N-Zone Max is holding your nitrogen investment into the field. You've reinvested your dollars so that more of that money is going to be put into your plants that are going to be then producing a final yield for you. So again, the brown line being that one which is found on the N-Zone Max treated, we see a spike each and every year following the final fertigation. What I want us to point out though is when we compare this to the light yellow line, which is going to be the untreated side, we have very little nitrogen that's actually being maintained at that 4-foot level when we compare that to our treated nitrogen side. So when we start to think about, well, what does that say for a big picture then? Well, for the big picture, that we go in and we actually sampled the groundwater. So we went in and we sampled the groundwater at 3 different years, and we sampled it throughout the year. And so as we look at the lines that we have here, the dark green dots are monitoring well 4. Remember, that was the end-zone max treated side of the field. The light green, as we're looking at it, is monitoring well 2, which is the untreated side. And what we found each and every year is shown in these red circles. So as we come in, we can look at this event starting at the beginning of June right here, starting at the beginning of June right there, and starting at the beginning of June all years from 2018 to 2020. And following that last application, we see that we are decreasing the amount of soil nitrates that are going to be found within the actual groundwater itself. Now, this would correspond to what we've been looking at in data, because over this exact same time frame, what did we see from the lysimeters at 4 feet? We saw that the soil nitrates were spiking at the 4 foot in the end-zone treated field, and on the untreated field, we were losing that. And this completes that story. So we see on the light green dots, we see a spike, light green dots spike, light green dots spike. The untreated side was allowing that nitrates to move through the sandy soil into that groundwater. So again, we're corresponding this with the idea that soil nitrates are being maintained within that rooting field. But I think this picture probably shows the best overall picture. So what we did is we went to the year 2020 and we mapped out again that soil nitrates at 4 feet versus the nitrates in the groundwater. And we paired those up so that we have the corresponding dates to one another. And when we see the end of our fertigation events, we're maximizing the amount of nitrates found within the soil profile, and at the same time, we're decreasing the amount of nitrates that is moving into the groundwater. So what does this tell us? It tells us we are maintaining nitrate right where the plant needs it to be. And also another thing that we want to think about is that this proves our XN technology. We are maintaining that placement. We're holding it right where your plant needs it. We're allowing you to reinvest your dollars, right? So 1 study over 3 years is great, but 2 studies over the same type of time frame is phenomenal. And that's what we find with our second study. So our second study was done at the Irrigation Research Foundation. You remember this was out in Yuma, Colorado. And what we found through here is that we looked at 2 different treatments, again, using end-zone max. So this is a really nice chart that we're going to come back to. So let's kind of take a look at what it looks like. So we set up the experiment utilizing 2 different rates of UAN. Everything on the left-hand side is the 100% UAN application. So you're looking at 40 gallons to the acre over that growing season. On the right-hand side, we came in and we reduced the UAN application by 25%. So this is 30 gallons. Then within each of our different placements, we had this idea of end-zone max, so 1 quart per ton, or a standard, which had no end-zone max. And then on the 75% side, we came in with end-zone max again at 1 quart per ton. And on the right-hand side, we had the control, which was 75% UAN with no end-zone max that was going to be added. All right, so now we really get a lot of lines. So let's stop and let's talk about what did we measure and how can we actually apply this to what we're doing. So first of all, when we set the experiment up, what we looked at was we measured soil moisture and ion movement. So soil moisture is just water. We're looking at pore water. Ion movement, when we think about ions, those are charged particles. So go back to nitrates. Remember, nitrates, NO3 minus, has a negative charge with it, so we can actually measure those movements. So what we did is we measured soil moisture, we measured ion movement, but we came through and we measured them then at 6 different depths. We measured them at 0, 10, 20, 30, 40, and 50 centimeters. So we oftentimes don't use centimeters, right? We're really comfortable with inches. So simply think about that there's about 2.4 centimeters in an inch. So when we are at 10 centimeters, we're at about a 4-inch depth. So when we start to look at the graphs, and I know that they seem really, really messy, but we're going to break those down. But just keep in mind that across the top is the control. So no end-zone max. This was the 75%, so the 30 gallons per acre. This was the 100%, so the 40 gallons an acre. And then down here on these bottom two, we have 75% but with end-zone max and 100 also with end-zone max. Then all of these from 0 to 50, these are simply the depths that we are measuring in either the water, the soil moisture, or that ion movement. And then all of the different colors, which are kind of pretty, right, are going to be all of the different depths. So blue is going to be 10, going all the way to green at 50 centimeters. So once we collected this data, we kind of stepped back and we thought, all right, let's see what story just looking at soil moisture can tell us. So as we start to think about this idea of soil moisture, let's talk a little bit about what happens when UAN is added to water. So when we add UAN to water, it actually lubricates that water. You can almost think about it as an oil, right? It's going to help it move down through that soil profile. And so when UAN is added, a lot of times what we see is the velocity of that water movement is actually increased as it percolates down through that soil profile. When we started to look at the untreated, again the top two versus the treated at the bottom, we saw a really interesting pattern come up. And what we found on the untreated was this dark green line always had the greatest amount of moisture. That dark green line was the 50 centimeters, so it was the furthest down from the soil profile. We also saw massive swings. Each one of these spikes was an irrigation or rainfall event, and so we saw this massive movement down. Well, if we think about nitrate and we think about that negative charge, if water's moving down very quickly and in a large volume, it's going to be carrying nitrogen away. When we looked at the end-zone max treated side, the spikes are much, much lower, which tells us we're moving water slower through the profile. But that wasn't the only thing that we saw. We also saw that the maximum soil moisture was at 40 centimeters instead of 50 centimeters. Why is that important? Because remember, UAN lubricates water. What does our XN technology say? It holds nitrogen in the rooting zone. So what we're seeing is that we're holding on to that nitrogen so much that we're actually altering the water movement through the profile, and we're maximizing that water availability. So then we started to really dig in and look at what are going to be called deltas. All right, so at first, this chart looks just kind of overwhelming. So let's stop and let's take a look at it. So first of all, going on these top two, outlined in the red, this is the untreated. UAN with no end-zone max. Down here in the green, we have our UAN that's been treated with end-zone max. The top row on each one is still that 75%. The bottom row on each one is still going to be that 100%. And then each one of our columns, as we come down, is the 10, 20, 30, 40, 50 centimeter depth. All right, so a lot of points, a lot of data that's going to be put in, but we're using this word delta. So what does delta mean? Delta measures that movement. So as we start to think about how do we interpret this, let's just come up here into this red circle, right? So we know that when we're looking at the red, it is the untreated UAN. When we look at it, what we notice is all of these dots that are scattered up, a few dots scatter down, but most of them are pushed all the way over to the right. So when you see dots that are scattered up, that's telling us that water is moving very quickly downward through the soil profile. Definitely not what we want when we're thinking about a soil nitrate. Also, as we move further to the right, what that is telling us is that it's a greater concentration. So not only am I moving water down through that soil profile because the greater concentration down through that soil profile when we compare those to the other side. So if we look at the 40% down at the bottom for the end zone max, we see very little movement and everything is shifted more of the center line versus being shifted to that right hand side. So let's take a look at the trends, right? Because it's really the trends that are going to tell us the story. So as we look at the 100% application rate and the untreated side, so no end-zone max, what we notice at all levels, 10, 20, 30, 40, and 50 centimeters, are dots way up toward the top and dots that are found way over to the right. So again, what does that tell us? As the dots move up, it tells me my water is moving down. As my dots move to the right, it says over time my concentration is increasing. So again, we're watching water move very quickly through that soil profile. When we compare that trend to the bottom, where we have the idea of the UAN treated with end-zone max at 100%, what we notice as we move away from the surface, so 10 centimeters, 20 centimeters, 30 centimeters, our dots are much closer to the zero line, which says we don't have a change over time, and we do not see dots scattered to the right, which tells us our concentration change over time is also less. So the story at 30, 40, and 50 centimeters is that when we have our end-zone max, it is slowing down water movement and it's decreasing that concentration change over time. Why is that important? Because nitrate has a negative charge. It's carried in that soil water, and as that soil water percolates down through the bottom of the rooting zone, we are now losing our investment. So the end-zone max treated side reduces the magnitude and reduces the movement over time. So as we then want to think about, well, how does that change that we're looking at with water tie into ion movement? Well, remember, ions are going to be charged chemical particles. We're most concerned about this idea of our nitrate with that negative charge. What we find is a pattern that is very, very similar to water movement, which would make sense because as our water is moving, it's going to carry that negative ion down with it. So we see over time from the 10 centimeter, 20, 30, 40, and really way over here at 50 centimeters, way down within the soil profile, we're having massive movement down and very large concentration changes associated with that. When we compare that to the end-zone max, once we get past that 10 centimeters, so this is 4 inches right here, we're getting to 8 inches, we're about a foot right there. We see very few changes, which tells us that we're helping to hold your nitrogen investment right where your plants need to utilize it, and we're not losing your investment in the bottom then percolating out past that rooting zone itself. So what does this tell us then? So if we look at these results based off of what our XN technology tells us, this XN technology said what? That we maintain our placement. We have 2 studies over multiple years conducted by third-party research in Minnesota and Colorado that back up that we are maintaining that nitrogen placement. We are reinvesting your dollars and we are keeping that nitrogen right where you need that. So we're keeping the placement in the soil profile, we're reducing the movement of water, and since we're reducing the movement of water, we are also then loss of nitrates, and we're allowing the plants to be able to utilize that across the different treatments. So we've taken some time, we've looked at research projects in 2 different parts of the United States, conducted against multiple years in varying environments, and we have found that research backs up that we are maintaining our soil nitrogen placement. However, our XN technology doesn't just say we maintain our placement. Our XN technology also tells us that we do it without disturbing the soil microbiology. And so when we think about soil microbiology, I just want to ask you a question. How many articles have you seen in the last 10 years that have started to talk about biologicals? Bacteria, fungi, protozoa, all in the soil. It's all over literature now. I know that with my clients, when I've sat down, that's been some of the leading questions, is what happens when we add your product to a biological? Or what happens when we're adding your product to our soil? What is it doing to the natural microflora composition of that? And so when we start to think about this, I always want us to focus on this last question right here. How many microbes are in a single teaspoon of soil? Right, so a teaspoon is so incredibly small. So when we think about how much are we actually going to find, what are we dealing with, when you take a single teaspoon of soil, you find more microbes in a teaspoon of soil than there are people on the earth. And if that wasn't enough, when we go through, if we were to take all of the fungal filaments, so the fungus, the idea of this hyphae that are going to be growing in that soil profile, if we could string them all together from one single teaspoon, there are several yards of fungal filaments. And that's not everything. We could continue in and even look at the fact that we have several thousand protozoa. So the idea behind what are we doing with XN technology is we are maintaining our nitrogen dollars, but we're doing it by not impacting everything else that's cycling within that soil. We're helping to maintain the natural biological processes that we find. So let's take a look at a research experiment that was conducted up at Acres Research that's found up in northern Iowa. Again, conducted by third party. Again, I love that because it removes the bias, and it was a multi-year design. And from my standpoint as a research agronomist, I love it because there are also 3 sets of replications per year. So we can start to really get a good picture of what's happening. Overall, the idea behind this experiment was to help quantify soil bacteria. Not the idea that we can just say we are not impacting it, but we want to be able to show what is actually happening. So within each one of these replications across multiple years, we had 4 treatments. So they were injecting anhydrous ammonia. So we had one treatment was just 200 units of anhydrous. Anhydrous with Enzone GL. We had 200 units of anhydrous with a competitor, and then we had a control. The control is we just simply ran the knives through the ground, but we did not include any anhydrous in there. I love this chart that's right through here because it just reminds us of the significance of not disturbing soil microbiology, right? We're looking at this idea of tens of billions, right, of bacteria and fungi all interacting in a well-maintained soil profile. So let's start to talk about a little bit with terminology. So I really want to talk about 2 key words that we need to track through here. The first one is what is called colony counts. So colony counts is this idea that we go through and we continue to dilute our sample until we can count the individual colonies. Right, so we can see this dilution right here, 10 to the negative 1, 10 to the negative 2, maybe 10 to the negative 3. There's so many colonies we can't count them all. So when we think about a colony count, the idea overall is we're trying to count individual colonies that are being grown in a medium on a petri dish. We then also have this idea of what are called colony forming units, CFUs per gram. And so when we think about this idea of CFUs per gram, we can utilize this to calculate the total number of bacteria per gram of soil. It gives us a really good way to compare between our different treatments so we get a really good picture of what's going to be happening as we add this idea of the Enzone GL. So first of all, what do we look at with results? The big picture is this, which I think is amazing and I love. Enzone GL does not disturb soil microbiology. Now let me back that up with research. So when we look at the idea, what we're seeing here is our colony counts, and I average them across all of our replications, and I average them across years. And then we have our 4 different treatments. Anhydrous with just 200 pounds, Enzone GL added to the anhydrous, a competitor, and then the control. What we noticed when we compared our product added to anhydrous to our competitor is that our colony counts were 50% greater. So remember, colony counts gives us the idea of what are we seeing with our dilution factor on the petri dishes. But the take home is we were 50% higher on our colony counts than with anhydrous that was going to be treated with our competitor. So a really cool statement when we think about our XN technology. We're not disturbing soil microbiology. However, then we dug a little step deeper, and instead of just stopping at colony counts, we went all the way to our CFUs per gram. So let's talk about the axes again. Across the X, we have our anhydrous with 200 pounds, anhydrous with Enzone, our competitor added to control. And across the Y, we're looking at the average CFUs, right, as we're seeing it per gram measured in millions, right? So when we see this number right here for our Enzone GL of 4.5, it's not just 4.5, it's 4.5 million CFUs per gram. And what we found when we started to look at those individual counts and we worked at scaling them up from the dilution factor is that our Enzone GL treated anhydrous had 80% greater CFU counts than our competitors did. And in fact, I think this result is amazing. The Enzone GL actually had higher levels than the control, which had no anhydrous that was going to be added to it. And so this definitely backs up our statement that when we are utilizing Enzone GL, we're not only maximizing your nitrogen dollar, we are keeping that soil microbiology intact. So as we think about big picture overall, I love this statement. It says soils harbor the most diverse and most complex microbiome on Earth. When we think about biologicals right now, we have so much to learn, but we do know that we have to maintain the natural soil microflora. And so when we think about our XN technology, not only is it maintaining soil nitrogen, it's also not disturbing the soil biology. And so across multiple years, multiple replications, 4 different treatments, we saw that our colony counts when utilizing Enzone GL were 50% greater than any competitor. And we also found that when we looked at our CFUs per gram and we scaled those up, it was 80% greater CFUs per gram than when compared with our competitor. So again, we have a product that maximizes your nitrogen dollars, maintains your soil microbiology to allow you to reinvest in your operation.